Engine is a relatively new concept. It came from basically the Scots and the Cornish, the inhabitants of Cornwall, who were miners, and they had the need to desiccate wells to continue digging to lower and lower depths. And that's how the steam engine was discovered and evolved more than a century before James Watt. The steam engine was not invented by Watt. Watt invented the separate condenser, which increased the efficiency, very poor efficiency, to something less poor. And the so-called power of steam had been known in antiquity to at the time of Ptolemy, meaning Cleopatra and these people in Egypt, which was actually one of the remnants of the empire of Alexander of Macedonia. And so the idea of harnessing the power, the pushing power of steam, harks back to antiquity. But the engine, known as motor before that among the Latin speakers, has been around, okay? And it continues to thrive in your world, which is engineering. It does not appear in the speech and lives and pretensions of those who are in the so-called pure sciences. Engine. And it's palpable. Unlike force. They talk a lot about force. Force is you cannot see force, but you can see the effect of force, as in this example. The engine, the definition of an engine is the original one. It's a closed system, you got it, that experiences heat transfer, you got it, and work transfer, meaning the work transfer, for it to be an engine, must be out of the closed system. Meaning an engine delivers work to its environment. You, the user, are clever enough to be the first member of the environment to receive what the engine produces. Eventually, the environment receives everything in terms of heat rejection from you, the user. One cannot save power, that is physically. One can save it, I'll get to that some other time. The power is rejected instantly by Adrian's moving his legs now in animal motion. The power that came from the animal design, converting a portion of the energy available in the ingested food, converting that into the work that I can do, and whatever I do through movement is dissipated instantly, and I have something to show for that. It is my movement, meaning the change of position on this planet. Okay, so listen, ask questions. Ask questions in case you don't have, okay, sorry, comments, please, comments. But if your comments have question marks at the end, that's even better. All right, the next claim to contributing today is and that means I'm taking another look at the big tent called thermodynamics. The proposition that, let me see how I wrote it. I did not write it. The Carnot efficiency is untouchable or unreachable or unattainable, out of limits, out of touch. Improve my English, please. So Carnot impossible. And how do you prove this almost on the back of an envelope? Meaning, because of what I thought last night. Well, let's look at the Carnot engine. You're going to go home and say to your parents, you paid for me to go to Duke, and Professor Bejan knows only one drawing. He knows how to draw a square. And it's a poor square at that. And this is the heat transfer rate for which you pay. And so I call it QH, the temperature difference is this. And the power output is that. The difference, everybody knows, is Q dot H minus W dot. With you here, so happy that you are being helped, that you do not question where this W dot came, except for Sadi Carnot, who was a mechanical engineer I told you about. And then while questioning, came up with the answer that this ceiling value, I wouldn't even call it maximum, the supreme value is the heat input times 1 minus TL over TH, where both of these T's are expressed in degrees Kelvin, meaning on the thermodynamic temperature scale, where 0 corresponds to absolute 0. By the way, Kelvin was probably in his diapers when Sadi Carnot wrote his book. The so-called absolute temperature scale was known as the ideal gas temperature scale. But anyway, this was known. And now, step by step, how you figure out that to reach this level of performance is obviously impossible. And it goes to questioning the square that I drew. The square defines the so-called system in thermodynamics. I just called it is the engine, but the name is the object of your investigation and reporting. And the system also, at the same time, defines the rest of the world called the environment. In other words, the system is your baby. You defined it. And you defined it by making a drawing, meaning by drawing the square, which is called boundary. The boundary is how your personal story begins. And the boundary is a surface, imaginary surface. And you know from Euclidean geometry that a surface is a volume of zero thickness. In other words, this unlike the chalk that I deposited on the blackboard, which has a volume of chalk dust, this thing called surface has zero thickness. Okay, so these are the facts that are due to you, the thinker, the one who questions human ability to achieve this level of performance. And the way that I came up with this little story for today's third module on the blackboard was from the more aggressive position of first believing that this is true, and then asking myself how to milk this result more and more, or better and better. Well, obviously, if you imagine plotting this W dot versus what you might be able to vary in this drawing, which is the high temperature. The high temperature can be varied through the design of the so-called combustor, or the combustion chamber, in which you burn the expensive amount of fuel that you purchase. So this is a degree of freedom. It's up to you. Here's the shape of the fire, with you hopefully outside. That's you. And yeah, so what's this W versus TH? Well, the formula says this is the W of Carnot. 0. We all know temperatures cannot be lower than absolute 0. So we put here 0 as if we know what that is. We don't know because, by the way, what I'm showing here, proving this is, as I just realized, is identical to proving that absolute 0 cannot be reached. Then you'll So I just thought of this, okay? Yeah. In other words, refrigeration machines, no matter how perfect, cannot reach that because of what I'm going to show you. And this is TL, which is the ambient temperature. Even Carnot cannot deliver any power if TH equals TL, meaning that whatever I have to plot has to be above this abscissa from 0 upward. It turns out that this WC, which is of course proportional to 1 minus TL over TH, is a curve that looks like that. So that's Carnot. And the message to Adrian in the middle of the night is that if you want to take Sadiq Carnot to his word, you have to make a combustion chamber that burns hotter and hotter. So this is the way to dream, or that way. Is that realistic? I pendulate to the drawing, to the 0 thickness surface, and ask myself how true that is in this direction of thought toward higher and higher temperatures. First of all, boundary does not mean wall. So boundary does not mean wall. Wall has thickness. Here's the boundary. Here's a wall. You see? So you can keep the boundary, meaning the square drawing, but recognize that inside of it, and of course all around, if you want to contradict me, there is a material that provides, makes you see the so-called boundary. And that material is called the wall. And the more you go in the direction of higher temperatures, the greater the heat leak from top to bottom through that structure. So this heat leak, I'll call it Q dot leak, is as much a part of reality as anything else in connection with engines. So the hotter the hot end, the greater the heat leak. In fact, the simplest way to state that is that the heat leak is equal to a factor called thermal conductance, and then the temperature difference from top to bottom. And what does this mean? It means that the Carnot engine that delivers that power to you, the Carnot engine that delivers this power output, is using only a portion of QH. So this is the beginning of a relatively easy piece of analysis, because I didn't mean to insult you last time when I talked about your generation not knowing calculus, but at Duke University, people, of course, are very good at calculus. So you may quote me that way. So W dot C equals Q dot minus Q dot H minus this CH T H minus TL, obviously, times 1 minus TL over TH So that is what the Carnot engine delivers if you add to the argument the reality that the engine has structure and size. Structure means that inside the box you have more than one thing. You don't have a one color, you have two. And size is the relative amount of wall, again, relative to the rest. And then you take a look at this new AHA. It is a factor. It's a product which involves two factors. One is called Roman 1 and the other one Roman 2. And you can plot qualitatively in your mind the two factors. One is descending linearly as TH increases. And the other one is increasing when TH is increasing. So the other one is doing this. And they are supposed to be multiplied to give you the answer. And multiplied, it means that obviously the actual curve must start from 0 because of the second factor. And then because of the first factor, the real curve must descend. So you know that the Carnot engine with material reality will have this behavior. And by manipulating, I'll give you the actual answers in a second, you arrive at the conclusion that the hot end should be of a particular hotness called the TH optimum, meaning the best TH. And then if you believe this story too much, which I don't recommend, you predict the realistic Carnot power, the no realistic, it's theoretical, you can call it imagined, that corresponds to this discovery. Hot end temperature turns out to be proportional to TL, and the factor of proportionality is 1 plus Q dot H over thermoconductance TL to power 1/2. So yes, the hot end should be warmer than the cold end, but how much hotter? Well, if the leakage is minute, that means poor thermoconductance, a small capital C, that means a big factor, and that means a high hot end temperature. But the point of the whole exercise is that real engines have body, and the more you try to milk power from the hot end, sadly you run into this tail end of the curve of reality. So that's important to know. In heat transfer, the discipline, there are 3 modes: conduction, convection, and radiation. In conduction, the formula of foundation is the so-called Fourier law, which would say in this case that Q dot leak equals the conductivity of this brick wall times the cross-sectional area of the wall. So this thing here would be capital A divided by the length of the heat current travel, which is the vertical dimension, called L. So this is the thermoconductance, and then here you have TH minus TL. So this is useful to know. In convection, speaks of the design of the wall. In my drawing, when I spoke of bricks, I was referring to conduction. And by the way, there's also radiation. Thermoconductance speaks of size, the size of the wall, and the shape of the wall. And I'm prepared to show you in the simplest way how it does speak of those things. If, because the wall costs money, the wall has size or volume. The volume of the wall is A times L. And this is proportional to what pains you, money spent. The thing that spells out thermoconductance in conduction, so C in conduction is proportional to A over L. To prevent this real curve from tailing off too soon, you need a lower conductance. So you want this to be minimized. It doesn't mean minimized like say, taking the differential and then setting it equal to 0. To minimize is to opt for something smaller. So to make it smaller, while subject to fixed expenditure. And, well, what does that mean? Let me show you. It means that instead of A, here I write volume divided by L. meaning that my wish of decreasing the conductance is synonymous with decreasing 1 over L squared. And that means what? It means making an engine that is taller and taller physically, with skinnier and skinnier sides. Yeah. And this discovery, now that I have it on the blackboard, should remind us to allude to the corresponding lesson in refrigeration, the answer to which is that one cannot reach absolute zero, except in principle with a refrigeration machine so tall vertically that if the top end is the atmosphere, the bottom end of the machine should be pretty much, anyway, very, very deep into the earth, proving once again that the temperature down there is not burning hot. But that's another, okay, so it's okay to talk. I told you, this is not a funeral. You could just talk. If you are embarrassed, just start talking to yourselves, you know.